Hello, I'm Glenn Tepfer and welcome back to the blog Uncontained. Today I'm going to go through one of my pet peeves in the industry. I'm going to try and demonstrate using some conductive media and a holiday spark tester some of the issues we're seeing and misconceptions with electrical leak location testing. It's a great technology if used properly, but I'm getting a lot of calls and we're seeing a lot of things in the field that are questionable. So I want to try and demonstrate a few things. I have some conductive liner and some non-conductive liner. A conductive sheet like I mentioned. You can see the arc. It's conductive on one side, the other side's not conductive. Same thing with these liner. This is not a conductive sheet of liner, and this one is a conductive back sheet, should arc, it does. So we'll get started on a few of the things I want to get into here. All right, the first thing I want to demonstrate is how conductive backed sheet allows you to detect holes. It's a conductive back sheet. I'll show you here that it should arc. So it's conductive on the back side, which is the black side. So if you have a double black conductive, it's important to make sure you have the right side up, right side down, or it's not going to work very well. Might electrocute a few people. Here would be a non-conductive medium. So what would be done with a spark test, and this again is a holiday test, but I'm using it to simulate. But the wand, much larger wand in the field, would be passed over, and wherever there's a hole, it's going to complete the circuit and you're going to be able to find the leak. The other option is to have a conductive media such as a clay, conductive geotextiles, with a geomembrane that doesn't have a conductive backing, and you need to have intimate contact. So you would use different leak location methods such as the water puddle, water lance arc test, if it was a covered geomembrane, dipole survey. But you're going to have your electrical source above, passing it over, and you can see it arcs and it completes the circuit to the conductive media below when you come across a hole. Below the geomembrane, you're going to want a uniform conductive material. So if it's a compacted clay liner and you have dry patches that are excessively dry, you're not going to get the conductivity in those areas, so your test is not going to be reliable in those areas. So again, your preparation for the actual testing, the layer below, like a conductive line or the installation of a conductive media, is important. All right, the first one I want to demonstrate to you is a regular geomembrane, non-conductive backed with a conductive surface below it. So in this case, we have our conductive surface. Again, you can see it's conductive. We have our sheet of liner laid on that conductive surface. Again, it's not conductive. And you can see that there's intimate contact here. There's no gaps. So as you pass it over a hole, if you're using any bare geomembrane survey like a water lance, it's going to pass through the hole and complete the circuit like that. Now, when I add a wrinkle, and this is a minor wrinkle here, again, it's a non-conductive sheet. It's a minor wrinkle here where it's elevated off the ground. In this case, the conductive media there, less than a ½ inch, and as you pass it over, there's no arc. It's not going to detect the leak. I can try and do this without electrocuting myself maybe, but you can see it will zap and connect the circuit if the wrinkle is not there. So that's one of the big problems, is wrinkles and other things like bridging and non-intimate contact that causes air as an insulator, so the test does not record holes or penetrations. Okay, I also want to illustrate this using a different sample we have. Again, this is non-conductive back sheet. I'll run this on the edge. There's no arcing. And you can see if I hold this down here, there's non-penetrating damages that are really bad that needs to be repaired in the field. But if I pass the holiday spark tester over it, which represents water lamps or other bare geomembrane surveys, as well as the dipole, you're not going to be able to detect those type of damages because they're non-penetrating. Same thing with this bad boy here. There was a rock or something that was stepped on underneath the liner. There's a hole there. If we run this over, there's no arc. I'll try and demonstrate. I think I can actually get it to probably arc if it's a little closer here. And you can see there is an arc when the hole is closer. So even that little bit of dimple penetration can be enough to offset and not allow the test to register as a positive for a hole, especially if it's a rock. The rock's most likely going to be non-conductive as well, so you have a multiple issue there. And you can see on this drawing here, well, the photograph, you know, wrinkles are problematic depending on the heating and cooling cycle, so it's always important to take the wrinkles into account. For this one, I want to demonstrate conductive back to liner and the advantages you have with it concerning the wrinkle that we just seen on the non-conductive geomembrane. I'll get rid of my conductive media here, so we have a standard media. It could be conductive, not conductive, but for this purpose, we're relying on the conductive media of the geomembrane here, which you can see it arcs. It is conductive. As we pass the wand over, it's a flat surface. We're getting the arcing as you pass over the penetration. And then we have this piece here. It has a slight wrinkle in it. You can see maybe ½ inch or so. So it's not touching the underlying surface. That don't have intimate contact. As you pass the apparatus over, you're still getting your arcing because it's detecting the penetration because of that conductive back sheet. So even though you have a wrinkle, you're actually going to be able to detect those holes using your bare geomembrane methods, or potentially even covered geomembrane with a dipole method. All right, I have my conductive media back, and I'm going to use a non-conductive back geomembrane here. Conductive media, you can see it's conductive. And we'll look at the effects on different damages here. The P's represent penetrations. The P.P's are partial penetrations, so they don't go all the way through. And as would be expected, you're not getting an arc with a partial hole. That's a thumbtack that we pushed partway through. You do get a clear arc on the actual full penetration of the thumbtack. And then we have a scratch that's 20 to 30 mils deep in this liner. And as you pass it over, you don't get the arc because it doesn't go down to the conductive media. So after I go through the conductive liner, we're going to take some coupons on these just to look at if there's a difference in tensile strength, because that's one of the my biggest gripe about using the leak location and replacing visual observation is that these things exist and they're being negated in the field. All right, now I'm going to look at a conductive back sheet. Same thing. Again, it's conductive back sheet. It arcs from the back side. The black side down is conductive. And we have partial penetrations and full penetrations. And a partial thumbtack You can see that there's no arcing there. The full penetration, there's a clear arc. And then we have a scratch, again, 20 to 30 mils deep. And as would be expected, it does not reach that conductive layer on the back, so it does not complete the circuit, and therefore it's not registered as a flaw. When you use a conductive sheet, obviously any damage has to get back to that conductive backing, which I forget offhand what the actual thickness is. I think it's about 7 mils maybe on a 60 mil product like this, but I can't remember exactly. And I think each manufacturer may be different on the amount on the back, but that still allows you over a 50 mil scratch or depth to get before you get to that conductive layer. So it's a significant depth before you can get to that conductive layer. All right, I want to just take a look at how the tensile strength is impacted by these scratches. I have the sample that we cut out of the conductive liner that has a scratch about 20 to 30 mils deep. I'll load it into the tensiometer, try and get it square. You can see that the scratch is already making obvious when you bend it. This one, a virgin sample cut next to the scratch. And we'll run it at the 2 inches per minute. I know this isn't the standard dog bone test that the lab would do, but often in the field we make subjective analysis by running coupons just to compare and see what happens. So as we watch this, we can see what happens here with the strength and yield. The first one, the bottom one with a scratch, broke at only 85 pounds per inch, and only 9% yield. The virgin one without any damage, you're getting your typical yielding. I can't think of the word I'm looking for at the moment, but you're getting your typical elongation pattern, and it's continuing to elongate. It's got a strength of 163, and the strength is staying the same, but it's continuing to elongate, and that's what you want in a containment system, is you want the material to stretch and not yield like it did in this case. And we're to over 100% elongation, meaning it doubled. So I'm going to stop the test there. I've now loaded into the tensiometer the textured non-conductive back geomembrane. They're both 60 mil. Again, I preloaded it because it seemed to be pretty shaky. I'm trying to load and keep the camera, but you can kind of see here the crack starts just to the left of the silver lining, not a crack rather, but the scratch about 20 to 30 mils deep. So we'll put the test on and see what happens. I want to remind you again, it's not the dog bone coupon that you'd use and see in ASTM D6693. But you can see there, 97 pounds, clean break. That's what the scratch does, only 13% yield, not very much yield. You can see the textured, still, it's maxed out with its strength, 137, so definitely stronger, but in addition to the strength is the fact that it's going to continue to elongate under stress. And you're seeing that elongation in here. And let it go a little bit more. But this is what you want to see, is the elongation. I'll let it go to 100%, but it's clear. Again, it's HDP geomembrane. And so it's just showing the difference between material that is damaged and material that is not damaged, and the fact that using an electrical leak location, you're not going to detect those scratches, but yet they are going to be a significant issue for the long-term longevity of the geomembrane. Okay, well, we finished up with what I want to show you today. Really, in conclusion, I'm going to try and get the coupon out of here, but you're seeing good necking on virgin material that's undamaged in the field. Same with this white one that we went through. And, here's one that had a scratch 20 to 30 mils deep in the liner. Just like what was shown on this sample here, another demonstration piece we have. Partial penetration, they're not going to show up in a leak location survey, except on rare instances you might get an arc if it's pretty close to the conductive medium, but it's few and far between that happens. It does happen, but it's not reliable. But again, you can see the material's not yielding. It's going to fail in the long term if it's put under stress, and that's not what you want as part of a containment unit. So I just need to remind everybody that the leak location is a great technology. I think it should be used, but it's not a replacement for visual observation. It's not a replacement for construction quality assurance. And to be used properly, it needs to be set up properly, and people need to be mindful of a few of the limitations, such as the wrinkles that you'll often see. How do you mitigate those, and how do you get a successful leak location survey that's going to be accurate done? Things to consider, different times of the day, which method might work, things like that. So just had a lot of numerous questions and discussions on this issue, so I'm hoping that this helped clarify. Until next time, I'm Glenn with UnContained.co.